Hello. So this is lesson 6.2, solving linear systems using matrices. Ignore the B. We're just doing this one. So we've got many real world problems involve systems of equations, but most are multivariable systems. So examples of multivariable systems include air traffic control, scheduling stoplights around traffic patterns, how 3D printers extrude polymers to create models, robotics, and a multitude of engineering problems. So our techniques of finding solutions through graphing, addition, and substitution would be too lengthy and cumbersome to efficiently solve a multivariable system. So that's what we're trying to do here, or that's why we're doing this. Um, so we're going to use a matrix, which is an improved version of the addition method. It is also a convenient way to organize a two-way classification of data and a rectangular array of real numbers. So, just like we know, an example of a matrix would be um, this one right here. Um, we're going to define a couple of different things on matrices. Some of this we already did in 6.4. So, sorry, I've got something in my throat. Let me grab a drink. Okay, let's see if that helps. So first we're going to look at row matrix. That means that we have one row. So for example, um, we could have 3, 7, and 12. So this is the row matrix. Okay, I'm sorry. Again, something is caught up. So a row again is a horizontal. So as we can see, we've got column 1, column 2, and column 3 here. Okay, column matrix is going to be one column. So that one is a vertical. And we could do, for example, 24, 50, and 10 in a column matrix. So we have one column and we've got one, two, oops, that should be a 2, and 3 rows. Um, Matrix size and order, that is the number of rows by the number of columns. So R times C. So for example, the original one that we did here, this has 2 rows, row 1 and row 2, and 1, 2, and 3 columns. So it is 2 by 3. Our row matrix, the size or order is 1 by 3. It has 1 row and 3 columns. And our column matrix, the size is 3 by 1. So it has 3 rows and 1 column. Okay, next we're going to look at a square matrix. So a square matrix is a matrix that has the same number number of rows and columns. So for example, we can do a 2 by 2 like this. That would be a square matrix. It is shaped like a square. Next one, we're going to look at what's called an augmented matrix. So a augmented matrix represents a system of equations. So, for example, if we have 2x plus 3y equals 4 and negative 7x minus y equals 12. Now, notice that we've got two variables and two equations. So what we would do is we would take the coefficients. So we've got row 1 and row 2. So our first equation goes in on row 1 and the second equation goes on row 2. And it's the coefficients that we're going to take. So our first column is going to be the x coefficients, so 2 and negative 7. Our second column is going to be the y, the coefficients of the y, so 3 and negative 1. Then we're going to draw a straight line, and our third column is going to be our constants, so 4 and 12. So C1 is x, C2 is y, and C3 is the constant. The straight line in the middle is the equal sign. Okay, now, next we're going to look at identity matrix. So an identity matrix is where we have ones on diagonal and zeros everywhere else. And this is except the augmented. What am I writing? Augmented column. So, for example, we've got our row 1, row 2, and row 3. We have our x, y, z, and our constant. That's our augmented. Actually, it doesn't go that far up, like this. So we would have 1, 1, and 1 here, and zeros everywhere else. Except we can have the constants can just be, or are going to be, you know, whatever numbers we've got. So what we can do here, since this is 1, it means that we have x equals 5. This one is y, so y equals 6, and z equals 7. So that is why we want to sometimes get into or make sure that we have an identity matrix, because we can actually solve the system of equations with that. So we can say that x equals 5, y equals 6, and z equals 7. So there's two ways of writing it. I wrote it as x equals and so on, and then I wrote it as a ordered triple, because we've got x, y, and z. Okay, so let's move on. Note matrix notation should be square brackets, but the equation editor did not do that on here. So every single one of these should be a square bracket here, like that. All right, so we're gonna go ahead and write the system represented by the given augmented matrix. Remember, this first column is x, second column is y, and the augmented column is the constant. So we can write, we don't write the 1 in front of the x because we know that it's there. But we're going to do 3y equals negative 5. And then our second equation is the second row, which is 2x minus 3y equals 1. And that is our system of linear equations for that augmented matrix. Same thing here, x, y, and constant. Now, since the coefficient or the coefficient for y would be a 0, we don't need to write it. We can just write x equals 7 and y equals 4. Next one, we've got 4 columns, or 3 columns and the augmented column. So x, y, z, and constant. So our first equation is going to be that first row, 2 times x plus 5y plus z equals 2. Second row is negative 3x. Now this one again is 0, so we can leave that as a blank. And plus 4z equals negative 1. And then our third row, 4x plus 5y plus 2z equals 3. Okay, now we're going to look at solving these. So one way to solve the systems of equations here with the matrices is back substitution. Again, all of these should be. Okay, so back substitution use a partially constructed identity matrix to work backward and solve the system. So if we look over here again, we've got x, y, and our constant. So we can go ahead and write the first row as an equation, x minus 2y equals 8. Our second row, the coefficient is going to be 0 for x, so it's just going to be y equals 21. So what we're going to do here is we're going to go ahead and substitute the 21 in where we have the y. So x minus 2 times 21 equals 8. And we go ahead and solve. We get x equals 50. So our answer for this one is going to be our x is 50 and our y is 21. So it's an ordered pair 50, 21. Okay, let's look at this next one. Well, that was a straight line. Okay, so again, we've got x, y, and z because we have the 3 columns plus the augmented column. So let's look at writing these as equations. We're going to start with row 1, x minus y plus 2z equals 9. Row 2, it's a 0 for the x, so it'll be y minus 2/3 z equals 0. And then our third row, we've got x and y coefficients are 0, so it's going to be negative z equals negative 3. So what we want to do here is I'm looking at this one right here. We only have z. So what we can do is we can divide both by negative 1, and we get z equals 3. So what we want to do with this is we want to substitute it in here into the second equation because that only has y and z. So when we rewrite that second equation, so y minus 2/3 times our z, which is 3, equals 0. Now, the 3's cancel each other out, and it's going to be a 1. So y minus 2 equals 0, y equals 2. Now, what we can do is we can plug in both the y equals 2 and the z equals 3 over here in our first equation. Okay, so we've got x minus our y, which is 2, plus 2 times z, which is 3, equals 9. So x minus 2 plus 6 equals 9. X plus 4 equals 9. X equals 5. So our order triple for this one is going to be x first, y then, so 5, 2, and z is the last one. So x, y, and z. Okay, now, next we're going to look at what's called Gauss-Jordan elimination. So what we're going to do is we're going to use row operations to simplify an augmented matrix until you have the identity matrix. So remember, the identity matrix is where we have ones on the diagonal um, over here, and then we'll have C1, C2, and C3. Or you can stop and use back substitution. That is the other option. So it's either whichever one comes first, whichever one is easier. So when working to get the identity matrix, finish the first column before you move to the next. Get the 1 in place, multiply by the reciprocal, and then get the zeros, add multiples of a row to replace a row. So remember what a reciprocal is. So for example, if we have 3/5, we flip it over, so a reciprocal would be 5/3. If we have a whole number 4, we can rewrite this over 1. So flipping it over would be 1/4. Okay, so let's look at 3 row operations you can use. So our first one is that we can exchange rows. So if there is already a 1 in the first column, just rearrange the 2 rows. So what we're going to do here, so we have row 1 and we have row 2. So we're going to exchange row 1 with row 2. So we're going to write the row 2 on the top, 1, 3, and -5. And then row 1, where row 2 was, 2, -3, and 1. So we can see that now we've got that 1 on the left as a diagonal, or on the left first row. That's what we wanted to do. So next step is to multiply a row by a constant. So multiply by the reciprocal. Not sure why that was a struggle, in order to get a 1. So if we look at what we've got right here, what we would want to do, so again, our goal is to get a 1 right here. So what we want to do is multiply by the reciprocal of this element right here. So half times row 1. Now, when we're multiplying, half times 2 is 1. Half times -3 is going to be -3/2. And half times 1 is going to be a half. And again, our goal was to get a 1 right here, and that's what we got by multiplying. So those are just 2 different options if you cannot do the exchange of rows, what we just did. Okay, now that we have that 1 there, now we need to, or what we're going to do is we're going to add multiples of rows. Use this to replace rows to get a 0 where you need it. So our goal here is to get a 0 right here. So what do we want to do? We want to um, take, so our row 1, as you can see here, has not changed. So we're keeping that the same because we want the 1 where it is. Our goal is to get a 0 in that second row, first column. So we want to multiply row 1 by a negative and then add row 2 on it. So what are we doing here? We're taking this one right here. So we're doing -1 plus row 2, which is 1, and we get a 0. So there's our 0 that we want. Well, we need to do it to all the elements in row 2. So we're going to take, again, a negative of the row 1 second column, so -3/2, plus our row 2 second column. Again, we're working on the second column right now. So adding 3 to it. So we get, these cancel each other out, and we get 3 and 3/2, which is 4.5. Now, we're going to actually rewrite it as a improper fraction, which is 9/2. So this one here is 9/2. Now we have the augmented column. So we're going to take the negative of the first row augmented column element, so a half, and we are adding the second row augmented column element to it, so -5. So we get -1/2 minus 5. So this ends up being -1/2 minus 10/2, because we need the same denominators. We get -11/2. So this column right here is -11/2. Okay, so a note, remember to finish the first column before you move on to the next. So our goal was to have 1 and 0 in the first column. We are done now with the first column. So now what we would do is we would continue this. So we would continue with the matrix that we've got here. So 1, 0, -3/2, 9/2, and our augmented column is a half, -11/2. Our next goal would be to get a 1 over here. So for us to get a 1, we need to multiply by the reciprocal of this. So 2/9 times row 2. So our first row would still be the same. So that would stay as 1 -3/2 and a half. Our second row, first column, is going to stay as a 0. We're multiplying a 0 by 2/9. That's not going to change. 2/9. So 2/9 times 9/2. These 9, 9 and 9 cancel, and 2 and 2 cancel. So we get a 1. And then 2/9 times -11/2, that's the augmented. The 2's cancel, so we get -11/9. And that was our goal here, is to get this as 1. We still have this as 0. So what we can say now is that y equals -11/9. And from here, we can plug this back in to the first one and solve for x. That's what this means. It's just showing how things are done. We're actually not finishing this whole thing. So But now we're going to start working on the next problems, and we're going to actually go ahead and solve these. So rewrite the system of linear equations as an augmented matrix, then use row operations to create the identity matrix and solve. Um, so our augmented matrix here is going to be our first equation here is going to be our row 1, and then we've got row 2. So 2, -4, and the augmented column is 16. 3, 1, and 3. Remember X, Y, and Z. Okay, our goal is to get this element right here as a 1. So what we want to do is we want to multiply by the reciprocal, which is a half. So we're multiplying row 1 by a half. So half times 2 is going to be 1. Half times -4 is going to be -2. And half times 16 is 8. And our row 2 does not change. Okay, next one. So we have a 1 right here. Next, what we want to do is get the 3 to a 0. So what we're going to do, and what usually works, is take the opposite of this element right here, which would be a -3. Multiply row 1 by it and add it to row 2. So what happens here? Our first row does not change. It stays like it is. It's our second row. So this um, right here tells us that we are changing the second row. So we're adding that first row to the second row after we multiplied by -3. So what are we doing? -3 times 1, that's this one right here, and then adding +3. So -3 plus 3 equals 0. So we get a 0 right here, which was our goal. Now we need to continue. So -3 times the first row, second column, which is -2. And we need to add the second row, second column to that, which is 1. So we get 6 plus 1, which is 7. So 7 goes here. And now we need to do the same thing for the augmented column. So -3 times 8 plus the row 2 augmented column element, which is 3. So -24 plus 3 is going to be -21. So the -21 goes here. Okay, so far we've got this right here. Now, identity matrix, next step would be to change this one right here to a 1. So we're going to take the reciprocal of that 7, which is 1/7, and multiply that by our row 2. So our first row does not change again. We keep it as it is. Our second row, 1/7 times 0 is going to be a 0. 1/7 times 7 is going to be 1. And 1/7 times -21 is going to be -3. Now we can see that we're able to write with this row, the row 2, we can actually write y equals -3. Our first row would be x minus 2y equals 8. And what we can do is we can plug this negative 3 into where we have the y. So x minus 2 times negative 3 equals 8. So x plus 6 equals 8, x equals 2. So we get x equals 2 and y equals negative 3. Our answer for this one is going to be 2, negative 3. Okay, next one. Again, same thing. Rewrite the system of linear equations as an augmented matrix, then use row operations to complete the first column of the identity matrix. And notice that this is just asking the first column, so nothing else. Okay, so let's go ahead and, write this as augmented matrix first. So 2, negative 6, 4, and 10, 1, 5, and negative 5, and 0. Sorry, I keep touching something. 3, 4, hold on a second. We are missing y here. So y has to be a 0. Coefficient of z is 4, and then 7. We need the augmented. There we go. So be careful and make sure that these are in the correct order as well. So that yours, we've got X, Y, and Z, that you've got them in the correct spots. Okay, so we need row operations to complete the first column. So again, what we want to do is we want to make sure that we have that first first row, first column element as a 1. What we're going to do is we're going to multiply by the first row by the reciprocal of that first column element, so a half. So when we multiply that by a half, we get 1, negative 3. Half times 4 is 2, and 10 times half, or half times 10 is 5. Now, the other rows did not change, so they stay the same. Okay, so again, we have the 1 over here. We're going to keep that, and we're going to continue. So now we have a 1 and a 1. So what we want to do is we want to take the opposite of the first row. So negative 1 times row 1 and add it to row 2. Our first row does not change. Again, this shows that we are doing the addition to the second row. So we're going to take negative 1 plus 1, that's going to end up as a 0. Negative 3, negative 3, so that's a plus 3, plus 5 is going to be 8. And then negative times the 2 minus 5 is going to be negative 7. Negative 5 plus 0 is going to be a negative 5. Row 3 is not going to change. Okay, so far what we have is we have a 1 and a 0 right here. We need this 3 again. So what we're going to do is we're going to take this first row, first column element and multiply that by the opposite of the 3, which is negative 3. So negative 3, row 1 plus row 2. Our row 1 does not change. Our row 2, actually, it should be row 3, sorry. Our row 2 does not change. It's the row 3 that we are adding on. So negative 3 times 1 plus 0, 0, no, plus 3. I'm sorry. We're looking at row 3. So negative 3 times 1 plus 3 is going to be a 0. So this is going to be a 0. So this is our element 1, 1, not 1, 1. It's our element, now I have a total blank out. It is the row first and then the column. Let me just make sure that I'm not saying this wrong before I say anything about it. We did this. Um, Hold on. Where? Matrix operations. Did we not look at the elements? Um, it's the row first. So 3, 1 is going to be a 0. Um, the next element, row 3, column 2, is going to be, again, -3 times -3 plus a 0, this one right here, and that's going to give us a 9. Next one is going to be -3 times 2 plus 4. So -6 plus 4 is -2. And the last one, -3 times 5, not the 7. We're adding the 7 to it, and we get -8. So this is -8. Okay, our goal was to get our first column of the identity matrix. So that's what we did. And as you can see, this does require, some work to make sure that we're able to actually solve these things. Okay, now we're going to look at dependent and independent systems. So we have dependent system. Remember, we talked about these with the in 6.1 with the system of linear equations and possible solutions. So this is the same thing. Dependent system is infinitely many solutions. So what does this look like as a matrix? So we're going to go ahead and rewrite this matrix right here as a augmented matrix, and then use row operations to create the identity matrix. So we're starting with 2, 1, and 4, 4, 2, and 8. Okay, so our goal is, again, to get this one right here to a 1. So what we're going to do is we're going to go ahead and multiply by the reciprocal. So multiplying the whole row 1 by a half. So 2 times a half is 1. Half times 1 is a half. 4 times a half is a 2. The second row did not change. Looks like this. Now, what we're going to do, we need a 0 here. So what we're going to do is we are going to multiply the first row by the opposite of this number here. So -4 row 1 and add it to row 2. Our first row does not change. It's the second row. So -4 times 1. Let me do it here. -4 times 1 plus 4. So this one right here, that's going to be a 0. The second column, -4 times a half plus 2 is, again, -4 times a half is a -2 plus 2 is a 0. Our third column, -4 times 2 plus 8 is going to be a 0. So what just happened? We got zeros all the way through here on the second row. So the last, or the second row here tells us that it is 0 equals 0. So this one, 0 equals 0, is always true. That means that it is a dependent system, and it means that we have infinitely many solutions. Um, we can either say infinitely many solutions, or what we can do is we can take, for example, the top one here and say that x, ordered pair xy, is such that 2x plus y equals 4 and close the braces like this. So that is what an a dependent system looks like. Next, we're going to look at inconsistent systems. So remember, it was no solutions. So we're going to look at what happens with this matrix right here. First, before we can rewrite it as an augmented matrix, notice that we have x equals and y is on the other side of the equal sign. So what we need to do is we need to rewrite this so that we move the x to the left side of the equal sign. In both cases, well, the y here and the x here. So negative 2x plus 2y equals 5. So these are our two, or the linear equations, so that we can actually write it as an augmented matrix. So now we're going to write it as an augmented matrix. 1, negative 1, and 3, negative 2, 2, and 5. Now, we already have a 1 here, so we don't need to do anything about that. We want to get this negative 2 to a 0. So what we're going to do to this one is we're going to multiply, since this is negative 2, we're going to multiply by the opposite, which is 2 times row 1 and add it to row 2. And again, 2 times 1 is 2 minus negative 2. Well, our first row does not change. It's going to be a 0. 2 times negative 1 plus 2 is going to be a 0. 2 times 3 is 6, plus 5 is going to be 11. So notice the difference here between these two. Here we got 0 equals 0. Here we get 0 equals 11. Well, that's not true. This is false, and it is inconsistent. So we have no solution. We can either write no solution, or we can write an empty set, a line through a 0. Okay, that's it for this lesson. Again, let me know if you've got any questions. Bye.